Before we begin this unit, let's remind ourselves about the Coulomb's law. So what it tells us is that like charges are going to repel and unlike charges are going to attract. The three types of bonding that we know about is ionic, covalent, and metallic. So 3.1 is about intermolecular forces. Previously, when we were talking about ionic and covalent, we were talking about intramolecular, as in the molecular forces that exist within the molecule. Now we're going to talk about how they interact with one another. How does one molecule interact with another molecule, which will eventually decide how they behave as liquids and solids. So there are three types of intermolecular forces. The first one is the LDF, which exists in all kinds of molecules, and it's also called a temporary dipole. They are the only forces that are present in non-polar structures. So think of a neutral atom, and what we know about a neutral atom is that, or any atom at all, is that the electrons are constantly revolving around the nucleus. Now, most of the times they would be equally revolving around the nucleus, but it also happens that for a moment in time, they gather on one side of the atom. So there will be a moment in time in which there is fewer or no electrons on one side and there's more on the other side. And that gathering causes a temporary dipole. So when the area where there's a lot of electrons gathering up, it's going to have a partially negative charge. And the other end, where there are fewer electrons, would have a partially positive charge. But then they would go back to normal again. This constant fluctuation in the dipoles is what provides these molecules to be able to interact with one another. Because when you have one side of the atom with a partial negative charge and it's interacting with another molecule that also in that moment of time has a partial positive charge, they are gonna attract, they're gonna attract one another. And this is how they are going to stick together. This is why, or this is how non-polar molecules are in a liquid form. And every time we're going to talk about intermolecular forces, you'd notice that we talk about the boiling point a lot. Because if the intermolecular forces are very strong in the case of LDF, as in non-polar structures, the larger the molecule, the stronger the dipoles, hence the stronger sticking up together, and they would have a higher boiling point. If I compare the gas helium, its melting point, with the melting point of, for example, krypton. So helium boils at 268.9 degrees Celsius. So that is, negative 268.9 degrees Celsius, which means that is when it turns and evaporates into a gas. But when I compare that with krypton, it's a negative 153.2 degrees Celsius. So what I'm getting to understand here is that helium is turning into a gas sooner than krypton. And then if I talk about someone like a diatomic molecule of fluorine versus a diatomic molecule of iodine, if you look at the periodic table, you would know that iodine is way bigger than fluorine. And the boiling point for fluorine is 85 Kelvin. And iodine is 457.5 Kelvin. So I can just interpret from this data that iodine is taking a lot of time, a lot of temperature, a lot of energy is going to be required in order to turn iodine from liquid to a gas. This would be your summary, kind of.